This video lecture, the second one in the series of lectures on code optimization, we're going to focus on spilling the contents of a register to memory and why that is needed. Note that in register allocation, it's possible that the method that we use, which is to look at register allocation as graph coloring, might fail to find a coloring for that graph. And that doesn't mean that graph coloring is then the wrong thing to do. It's that what it's telling us is that maybe there is no valid way to assign all the locations to a register. In this case, we cannot hold all the values in registers, and so some of the values should be spilled to memory. So it's called spilling because it's essentially we don't have enough room for it, so we're going to keep it somewhere in memory and then load it when we need it and store the value back into memory. Note that in LLVM, we end up using a alloc for every location when we define it. And alloc is actually just storing the location in the stack memory. And so by default, everything is spilled to memory in LLVM. And then what we end up doing in LLVM is making sure that the ones that can be stored in registers are converted to be using registers. And the rest, the ones we can't assign to registers, will remain alloc so remain being retrieved from memory. So essentially in LLVM, you can think of it not quite as spilling to memory, rather everything starts off in memory and then some locations are promoted to using registers, which then makes the code run faster. So k coloring can fail. What if, for example, nodes have k or more neighbors? Then there's no way to assign k colors to every neighbor if you have more than k neighbors. So it just means that the k coloring is impossible. So if you want to find the k coloring of this graph where k equals 3, you find that that's not possible. It's not possible to assign 3 colors such that a node connected to another node by an edge has to have a different color from that other node. So in this case, if you look at C, this node C over here, it's connected to 1, 2, 3, 4 different nodes. And so there's no way that you can use 3 colors in order to provide different colors for every neighbor of C in this. So let's say you remove A. It's still not possible that you can get a 3 coloring for this graph being available. So what we can do first is what's called optimistic coloring. So let's assume that we can k color it and do the same heuristic that we did before, where we removed nodes, push it into a stack, and then pop each element out of the stack and assign them registers. So we're going to use the same algorithm, except we're also going to use it where we know that the k coloring might not be possible. And if it's not possible, then we pick a node as a candidate for spilling and remove it from the graph and then continue k coloring. And by removing this node from the graph, it might end up that the resulting graph now is k colorable. So what we're doing is essentially removing a node from the graph, storing it in memory, and the sacrifice of that node from the graph can maybe help the rest of the nodes in the graph to use registers. Or maybe it's possible now to do a k coloring of the register interference graph. So let's say that we removed F from that graph that we saw before and we continue. Then we continue as we did by removing the nodes one by one. So the ordering we have is the top of the stack is C, and then we removed, so C was the last node that was removed. And notice that we have this problem guy over here, this F, which had a lot of neighbors in the graph. So let's do the same technique that we did in the previous video lecture. We color these nodes. We start with the C, we assign it the first color or first register R1. It's connected to E, which is given an R2. And then we popped out the C and the E. We pop out the D and assign it R3, a different color from E and C. Then we pop out B. B is still able to get 3 R3 because it doesn't share an edge with D, so it can reuse that register. Now comes the problem node, which is F. If I add F, we hope that it will use less than 3 colors, but it may not. So in this case, it turns out it cannot. So F is not able to be assigned a register. It can't be R1 because it's connected to C. It cannot be R2 because it's connected to E. It can't be R3 because it's connected to B. And in fact, it's also connected to D, so it's doubly worse. It cannot use any of the 3. It really needs an extra register here. But since we don't have more than 3 registers, of course, this is a complete sort of made up example. I don't know if any CPUs that have 3 or less registers. Most will have at least in double digits, if not in triple digits. So the number of registers is unlikely to be that small, but it's a good illustrative example. In this case, F cannot be assigned a register. So what we do with F is we allocate a memory location for F. It's typically in the stack frame. Like I said, in LLVM, we would use alloc A in order to assign a location, a memory location in the stack. And we call this address in the subsequent example. We're going to call it the address of F as FA. Before each operation that reads F, you have to insert a load. So it loads the value from the address FA and assigns it to the location F. And then after each operation that writes F, you insert store. So you insert a store of the F back into this memory location FA. Spilling is expensive with respect to the time it takes to load and store, because it has to go out to memory. But it sometimes is the only way that we can get all the locations working. The main thing is that spilling one variable or one location might enable all of the rest to be stored in a register. So by spilling one location to memory might enable efficient register use for all of the other locations. So let's look at this example, which we've been using as an example before. Now in this case, if we are spilling F, so notice that we are using F over here, and then we're rewriting F here. So we're using it here, we are using it here, and we are storing it here. So whenever we use it, we have to load it. Whenever we store it at a location, we have to store it actually into memory. You can see here it's loading from the memory location FA and then assigning it to a temporary location F1, it's using that. Same here, it's loading from memory address FA, storing it in F3 and then using F3. Notice that F1 and F3 do not survive past this local block, this local basic block. It's not used anywhere else in the program. It's just for loading the variable from memory and then storing the variable from memory. So since I assign something to F2, I take F2 and store it into this memory location for FA. So this is what the code looks like after spilling F. Now, if you saw the liveness analysis from before, this was what we had done before, you can see that F occurs quite a fair bit in all of these different places. It needs to be carried around quite a bit. And now, as a result of spilling it, what we can do is get rid of F as a dependency. So F no longer needs to be alive at the same time as C, D, and E, or B and C, etc. As a result, what we end up with instead of F is using F1 here, F3 here, and F2 here. And notice that those are not the same variable. They're completely different variables. So as a result, their liveness doesn't intersect with each other. So in this case, we rebuilt the interference graph, except that F has been split into these 3 temporary variables or temporary locations. So each F1 or F2 or F3 is alive only between the load and the next instruction or between the store and the previous instruction. So spilling reduces the live range of F and therefore reduces the interference of F with all of the other nodes in the register interference graph, and therefore every node has fewer neighbors as a result. So some of the edges are removed, right? So in this case, notice that I've added F1, F2, and F3 instead of just a single node F. And the graph looks a lot less connected than it did before. There are not as many cliques of nodes connected to each other, thanks to the fact that the location F was spilled to memory, and therefore we use these 3 different temporaries in each of the basic blocks. So F interferes only with C and D, and the new register interference graph ends up being 3 colorable because there's no node there that has more than 3 neighbors. So sometimes you might need to spill more than one location. What we saw was an example where you had to spill one location, but you might have to do more in order to find an appropriate graph coloring of the register interference graph. So let's take another example. We're doing the same algorithm as before. We pick a node, we remove it, push it onto the stack, and we remove all of the edges from that node and the node from the graph. Let's remove C, remove B, remove E, remove F, and then remove D. And now that the graph is empty, we go and pop elements off the stack to create the register interference graph. So here we extract register interference graph. So D here is assigned R1, F is assigned R2. Notice that F could have been assigned R1 if F and D don't have an edge connecting them. That's one sort of heuristic one could use. But in this case, we're assigning it a different color because they're connected to E, which has the need for a new register R3. Then we pop out B and insert it back into the graph. And here, notice that B is assigned to R3 because it doesn't share an edge with E, which was previously assigned to R3. Now when we add C to the mix, C is connected to 4 different neighbors. So it's not possible to 3-color this graph because we're assuming, remember, that k equals 3. So what we do then is we spill C to memory, and then we go to the last one, which is A, which again cannot be colored because it has 4 edges, and each of the nodes it has an edge with has to have a different color. So R2, R1, R3, it's already taken up, right? So this one is already a problem because it's connected to 2 nodes that have the same color. That's fine because E and B don't share an edge, but we cannot reuse any of these nodes. F is assigned R2, D is assigned R1. So R1 and R2 are out, and R3 is out. So for k equals 3, it's impossible to do. So A ends up being spilled to main memory as well. There are many different heuristics to pick a node to spill. Like you can spill the location or temporary with the most conflicts, or spill the temporary location with the fewest definitions and uses. Or we also want to definitely make sure that we don't spill inside an inner loop. So if you have a while loop and a for loop inside it and a while loop inside that, doing a load and store in the innermost loop is going to make your program much slower than if it was outside of any loops. C allows a register keyword to direct the compiler whether a variable contains a value that's heavily used. Although in practice nowadays, it's better to let the compiler do the optimization rather than do the optimizations by hand. So it can be considered a hint, but programmers are often actually bad at giving hints to the compilers. Oftentimes they'll put everything as with a register keyword or not enough. In order to avoid the human error that happens, it's easier for the programmer to let the compiler do the optimizations and do the register allocation itself rather than rely on the programmer.